YouTube. Welcome to Mr. Oi's.
Shout out to all my subscribers.
Yes.
So anyway,
Make sure you smash that
This
like
is your boy,
button.
Mr. Oy here.
Make
Back
sure
at
you
it
get
again.
that bell, turn on the notifications.
second assignment is the fewer problems, but it's the harder of the two. It's the one where you're using the table to find the second derivative test, where you're using the table to find extrema, and maybe some points of inflection stuff too. Okay. All right. So let's do. So that's what we want to do here. We want to do kind of a harder problem, an exponential function problem where we've got to use our table to analyze what's going on with this thing. Okay, and let's go one step further. Even though these assignments are really only asking for, I can't remember exactly, but it's going to be relative extrema. Let's kind of go a step further in preparation for the next round of stuff we're going to do, which is curve sketching, which is everything, right? So we want to just use these tables to their fullest extent, get everything we can out of these tables. Eventually, we'll take a look at some problems when we get to, in our physical textbook, which we hardly ever use, it would be section 3.6, which is curve sketching. And then we're going to incorporate all the stuff we're doing right now, which is all the rows of the table, but we'll also add horizontal asymptotes, vertical asymptotes, slant asymptotes. We can do everything with these tables, right? And we'll just kind of put it all together at that point. All right, so what about this guy? What do we want to do first? You take derivatives, but before we even start doing that, we want to know
What's the domain?
the domain, right? We want to know where does this thing exist. So let's explore the function. We've got an x squared, which is fine, times an e to the negative 2x. Well, what's e to the negative 2x gonna, what's that all about?
It's a great question.
E to the negative 2x would be the same thing as, in fact, I'm gonna add an extra page here just for some additional notes.
Are you recording?
I am recording, thank you.
Citizen.
We're gonna smash that out.
Yeah, didn't merge coming? What's the name of Mr. Oi's subscribers?
So,
The oysters.
thank you, Reckless. Okay, so, what is e to the negative 2x all about? So e to the negative 2x is the same as 1 over e to the 2x, right?
Yeah.
What are the only red flags we gotta look for here are gonna be places, we gotta look at the natural domain of a function. But what about an exponential function? What does an exponential function look like?
It's a great question.
You know this one, right? You told me now, and I'll tell you how you know this one, because everybody confidently told me yesterday that a log function looks like this.
Yeah.
So I would claim that if you know what a log function looks like, you know what an exponential function looks like, because they're inverse functions. So they've got to have symmetry about the line y equals x, right? So the graph would be the reflection over that line. Just a little quick mental pop quiz here. Do you remember my special trick for graphing an inverse? 90-degree rotation counterclockwise, and then flip over the y-axis will always get you there, right? Instead of having to do the mental gymnastics of trying to reflect over a diagonal line, which is just tough for us to do. In this case, it's not so bad. But would you agree if you do that, you end up with something like that? And that's going to be the point 0, 1, right? Okay, so if we, so the graph indicates that the domain is all reals, doesn't it? Right? Okay. And notice here, just to throw another, just can't resist, another brief little review. We said that the domain of, if we look at the domain and range of the logarithmic function, right? The domain was positive values.
Yeah.
The range looks like it's everything, doesn't it? All reals.
It's just a function.
Yeah. Remember, all you're doing with inverse functions is swapping the domain and the range, aren't you? Makes sense. So now the domain is all reals, and the range would just be positive values of y, okay? So then let's, just a little more review. So what does it do if our original function, let's say, was e to the 2x? So e to the 2x would have just been an exponential function, right? Okay? So e to the negative 2x, all I'm doing is multiplying, essentially I'm just multiplying x by negative 1, aren't I? Now go back to like algebra 2. Okay, in algebra 2, what did you learn about this? If we have the function, my parent function is f of x, and g of x is f of negative x, what did that do? If I multiply x by negative 1, what does that do to the function? Flips it over which axis? The y. The y. Flips it over the y. So all this is doing then, when we do e to the negative 2x, is we're flipping it over the y-axis, and it's just going to do something like that. Okay? Does that make sense? Okay, so the exponential is, there's no problem with this, is there? Another way to look at it, if I put the e to the 2x on the bottom, the question is, well then, when would that equal 0? Well, when does e to the 2x equal 0? Never, right? It never equals 0. And even if you forgot that, if you were trying to find out, if I were trying to solve that equation, when does e to the 2x equal 0? How do I solve an exponential function?
Take the natural.
I log both sides, don't I? I log both sides to undo the exponential. And so my very next step would be 2x equals the natural log of 0, which blows up because 0 is not in the domain of a log function, right? And so we can see that's never going to happen, is it? Right? So, moral of the story, do we have any issues with this function? No, we're fine. We're fine. There's no place, neither one of those two factors ever create any problems, and so we're good. So the domain is all reals. Okay. All right. So when we draw our, let's take the derivatives first, because I don't know how much space I'm going to need to take the derivatives. Domain's all reals. We got that. I make kind of crappy infinities now. I don't know. That's hard to do for me. What about f prime? What are we going to get for f prime?
Well,
So what rule are you applying, Landon?
well, you got the product.
Product rule, right? You got a product rule, and then the derivative of 5 we don't have to worry about, but we got a product here. So I'm going to have x squared times, what's the derivative of e to the u?
E to the u.
Times
U.
u prime. Okay. So I'm going to get times e to the negative 2x times negative 2, right? So there's x squared times the derivative of the exponential plus the exponential times the derivative of x squared, which is, okay. And then I could factor this, right? Let's do that. So if I took out a 2x, actually I could take out an e to the negative 2x times a 2x, couldn't I? Yeah. Right? And so if I do that, what am I going to get? I'm going to put the positive term first. That's just 1, isn't it? I factored out the whole thing. Minus, now what's gone over here? The 2's gone, one of the x's is gone, and that's gone, right? So I just get minus x. Okay, so if I want to write that, I guess I could write it like this. 2x times 1 minus x over e to the 2x, how about? Okay, there's my first derivative. So let's analyze that one. Where are the critical numbers for the first derivative? So 0 and 1 would be the zeros of the first derivative, agreed? Okay, so then we could write f prime equals 0 at x equals 0, 1. Any place where it's undefined?
No.
No. No place undefined because we never divide by 0, right? Good? Okay, so moving on down to the second derivative then. So where do I want to pick up with differentiating?
Well, I would.
I do.
Stay with it. Green, right above.
Right above the green, yeah, we could do that, right? We could go to here in factored form if we wanted. Okay, that's fine. I mean, really either there or there, but there we're gonna have to do product rule. I mean, I don't know, either one, doesn't matter. Doesn't
I
matter.
mean, we're having a good product rule 3 times.
Yeah, yeah, you are, either way. You know, I might just go up to here, honestly. I think I would. 6 of one, half dozen the other, but I would probably just go here. Okay? And I'm the one writing, so I'm gonna do that. So if we differentiate this first term up here, okay, what am I gonna get? I've got my -2. I can just leave that out front, how about? So I've got -2 times whatever I'm gonna get from the product of those two things. But I already did that, didn't I? Didn't I? I mean, right, I already did that derivative. That's the derivative I did right here.
Oh.
You see that?
Oh.
Okay? So
So it's just the same thing.
So I'm gonna get, when I differentiate, everybody see this little trick? When I differentiate this stuff right there, that's it. Everybody get that?
Yeah.
Okay? So I've got my -2 times the derivative of all that stuff gave me this from the product rule, so I'm just gonna copy that down. X squared times e to the -2x times -2 plus 2x e to the -2x. Agreed?
Yeah.
Okay? Plus the derivative of this product. That's a little bit easier product at least, right? So what am I gonna get there? Plus, I've got I've got this, so e to the -2x times the derivative of 2x is what? 2. Plus 2x times the derivative of e to the -2x, which is e to the -2x times -2. Okay? All right, so let's collect like terms, and we should get some here. So if I distribute the -2, I'm gonna get a positive 4x squared e to the -2x minus 4x e to the -2x plus 2 e to the -2x, and I'm thinking this is gonna be a like term somewhere, isn't it? I'm gonna get a minus 4x e to the -2x. So those are like terms, aren't they?
Yeah.
Everything else is not though. So if we collect like terms, we get 4x squared e to the -2x minus 8 of those, right? I got -4, -4.
Well,
So let's draw a little line there. So that guy and
I
that
have
guy.
a question.
Yep, question?
Isn't the first term and the second term about those cancel each other?
That's an
Oh,
squared,
there's
that's an
x, oh, okay, I didn't see that square. Never mind.
And then we get this plus 2 e to the -2x. So let's go ahead and we want to factor this because we've got to find the zeros, right? So what can I take out?
2 e to the -2x.
Okay, good. 2 e to the -2x, leaving me with, what's that going to give me? 2x squared
Minus 8, or 4x.
minus 4x plus 1. And maybe we can factor that, yeah, maybe. Multiply to 2, well, we're not gonna be able to factor it. Let's see if some real, how do we check real quick to see if real zeros exist?
Discriminate.
The discriminant, good. So if we check the discriminant here, b squared minus 4ac would equal 16 minus 4 times 2 times 1, right? So it's 8. So what's that tell me?
But it,
Can't.
It makes sense.
Yeah, I do get real, they're not convenient ones, but I do get two real zeros, so I gotta find them then. Okay, but the good news is I already did some of the work, so we're just gonna use the quadratic formula, aren't we? Right, we're gonna set this thing equal to 0, and we're gonna find that, oh geez, how did I do that?
What happened?
That's another glitch,
Whoa.
glitch in the universe. So f double prime equals 0, and I guess let me say one other thing. Would I even need to find the zeros of the first derivative if I were just looking for relative extrema?
No.
I wouldn't, right? Because all I need to do is apply the second derivative test, so I wouldn't need to, this is superfluous if I'm answering the question that's being asked, but we're going the extra mile like we always do, right? And we're gonna find the inflection points also, okay? So f double prime equals 0 when this function, or this factor equals 0, right? So let's just apply the quadratic formula. When x equals negative b plus or minus the square root of the discriminant, which we already calculated, divided by 4, right? Okay? And if I finish that up, what am I gonna get here? So that's gonna give me,
2 plus
so I'm gonna get 1 plus or minus 2 radical 2 over 4, so that's gonna be radical 2 over 2.
Yes.
Okay, so those are my two zeros of the first derivative then, okay? So this is kind of a mess. It took a whole page just to calculate, to find my critical numbers. Let's summarize those in a table on the next page. So you guys have to remember this. Somebody write this down. My first derivative critical numbers were at 0 and 1.
Yes.
Okay, and the second derivative critical numbers were at 1 plus or minus 2 radical 2, or square root of 2 over 2. All right, so our table. Let's do. I need to take some pictures.
Same answer.
Wait, who'd you say?
Oh, yeah, I remember his name like
Who was he?
So there's f prime from the first page, then we need f double prime in a convenient form, which is right
Who's he gonna-
there, I guess, right? Okay? Yeah.
Pretty much. Pretty much.
It's just a fish, it's like balls. And then the other.
But you have to be able-
Yeah, the math.
Pretty much. You sounded so apologetic about that. Remington just like.
Gasp.
I was, yeah. That's what happened.
Okay, for our table then, we had,
Yeah, I know.
so my domain we said was all reals. What were the critical numbers again?
0, 1.
Okay, so 0 and 1 were critical numbers. Those were zeros of the first derivative, right?
Right.
Yeah.
Okay? And then we had 1 plus or minus square root of 2 over 2.
Correct.
Okay, so 1 minus square root of 2 over 2 is going to fall in there somewhere, right?
Yes.
That's a 0 of the second derivative, and 1 plus square root of 2 over 2 is out here somewhere.
Yes.
Good? All right, so now how do we use our table most efficiently here?
Well, we want to,
We need another test point.
And 1 in
There you go, right? So we want to know what goes there and there. And that's gonna tell us almost everything we need to know. We're only gonna need one test point over here somewhere to see if the concavity switches, and that's it, right? And know, pretty much everything about this function. So, let's see, so if we want to evaluate our second derivative at 0, that's easy to do. We can plug it in right here, right? So f double prime of 0 is gonna give me 2 times e to the 0, anything to the 0 is 1. So I'm getting positive times positive, because those go away, right? So I get positive. So what does that tell me about the nature of that guy?
It will open up.
So opens up and I have 0 first derivative. So we know we have to have a horizontal tangent and an upward opening function. Okay, so it's minimum, it's a happy function, right? If we evaluate the first derivative at 1, what are we gonna get? So if I evaluate it at 1,
Are you going to the first or second?
second derivative, sorry. Second derivative at 1, we're gonna get 2 times e to the negative 2 is just, that's positive, isn't it?
Yeah.
Okay.
Just full differential.
Times, what about here? Now this one, we gotta do a little calculation, so I'm gonna get 2 minus 4 plus 1 is negative. Okay, so then, we know this is a sad function. And we know something about this guy.
That's the inflection.
That's the inflection point, right? And we could even, well, no, I'm not gonna do it. We even know kind of what that's gonna look like too, don't we? Right? It's gonna be transitioning from concave down to concave up. So if you wanted to, you could even maybe do something like that if you wanted to, right? You don't have to. And then we need one test point out here, so let's pick something convenient like 10. And at 10, what are we gonna get? I'm gonna get positive, and pretty clearly this is gonna be positive, isn't it?
Yeah.
Because I'm gonna get 200 from that term and small stuff from that one. So I'm gonna get positive. Whoops, there. So that also is an inflection point. Okay, and so what's that one gonna look like? That one's gonna be from concave up to concave down. It's gonna do something like that. Right, and if we knit all those together, we get our graph. To make things just a little tidier, we could plug in some values, like if we wanted to know, for example, the extrema, right? We had extrema here and here. You know, we could just plug 0 into our function, because that's easy to do. What do we get if I plug 0 in? Just 5? Okay, so we get the point. 0, 5, and if we plug 1 in, we're probably gonna get something weird. I'm gonna get 1 over e squared, right? So 1 over e squared is gonna be like 1/4-ish, 1/5, something like that, right? Plus 5, so I'm gonna get something a little bigger than 5, but not much. So, just like, I don't know, 5 point something. And if we graph those on our function up here, we get 0, 5, and 1, 5 point something. And we gotta have the curve do this stuff. So it's gonna be a minimum here. And the concavity's always up to the left of that, isn't it?
Yeah.
Right? So we know the function's gonna do that forever. And then here it's gotta change concavity and go down. And then it's gonna change again out here at 1 plus square root of 2 over 2, so that's like 1.4-ish. So out here somewhere, it's gonna flip around and do that. But it never turns up again, right? Or we would've had another critical number. So there's our stems, that's pretty cool, we can do that. Right? These are, just kinda, you have to embrace your inner nerd a little bit here and just have fun with these, because it really is, it's like a puzzle, it's like a math puzzle. being able to put all this stuff from the table together and create a, a sketch of the curve, there's something really gratifying about that when you get it right. I mean, it's not gonna be perfect, but we don't need it to be perfect. We just need to be able to identify what are the important places on the function, right? Where are those? But the rest of it, we just want a basic idea what it's doing. Okay? Make sense? Okay, good work.
Works